Hi everyone, I'm going to be trying to do a video today on chapter 9.1. Basically, it's just a recap of what we learned last time on Thursday because a few of you missed last time, which is pretty reasonable, I suppose. But in any event, let's cut to the chase. So 9.1 is an intro on differential equations. All of chapter 9 discusses differential equations, but 9.1 just discusses the intro of what they are and how the mechanics behave, basically. And the first thing I want to talk about are algebraic and differential equations and the difference between them. So algebraic equations are the ones we kind of know and love. Powers of x, basically. You could possibly have sine of x in there, e to the x. So trig and exponential equations are technically considered kind of algebraic in the sense that you solve for the variable. So in these types of equations we're used to, we solve for the variable. Whereas here in a differential equation, we don't solve for the variable, we actually solve for the function. So here you may be given derivatives of a function and maybe multiples of that derivative. Let's say f of x minus 2 equals f prime of x. Something like that, just an equation involving derivatives. It doesn't really matter, this is just an example. But the goal is to solve for the function, not the variable. And you may possibly get multiple things. There may be multiple solutions, like here there are possibly multiple solutions. Okay, so here's a particular example of a differential equation, and this is kind of a simple one. It says f prime of x is equal to e to the x minus 3 x to the third. And how we're going to solve this is, well, how do you get rid of the prime in f prime of x equals? You just antiderive. So the antiderivative of f prime is just f. Antiderivative of this is e to the x itself minus, I guess, 3 over 4. Let me write it like that, 3 over 4. X to the new power is 4. And now plus c. And now this is what is called a family of functions because c can be anything really. So what we can say is this solution to this differential equation, there's actually infinitely many because c can be whatever. C can be 5, 0, 100, and it would still be a solution to this differential equation. Okay, so that last example we saw was actually a first order differential equation. Order just means that the highest power, well, in this case actually not power, highest derivative that's involved. So that was first order because the highest derivative was first derivative. Here, this is y double prime, so this is an order 2 differential equation. Even if this was a prime here, the highest derivative is still 2, so it's still considered a second order, regardless. But in this case, I want to look at y double prime minus y equals 0. And it's less obvious, but I'm just going to tell you that y equals e to the x is a solution. And how can we check that? Well, here's how we can check it. We can find all the derivatives involved and then plug it in. We can find all of the derivatives involved and just plug it in. So when you find the first derivative, you get itself. When you find the second derivative, you get yet again e to the x. Plugging this in, we get e to the x minus y, which is also e to the x. That's indeed 0, so it's a solution. Another solution, actually, believe it or not, is y equals e to the negative x in this particular case. Why is that? Well, again, we can check by finding all derivatives necessary that are mentioned in the differential equation, basically. Of course, to get to the second, you have to jump through the first before. So the first derivative is negative e to the negative x. Second derivative is, well, another negative comes down, so it's positive now e to the negative x. So plugging this into the differential equation, we get y double prime, which is, I guess, e to the negative x, minus y, which our solution is e to the negative x, equals 0, and that's definitely true because anything minus itself is 0. So these are two solutions to this differential equation. Okay, so we'll be taking a look at now at an application of differential equations. This one I want to take a look at in particular involves population growth. And here we say that, it is said actually that one model of population growth assumes that the rate of growth of the population is proportional to the size of the population. And, well, if we let p equal the population size, and we let t equal time, one way to describe this sentence, I guess, by a differential equation is to say that the rate of growth, which is, well, the rate, well, it should remind you of derivative. So it's dp dt equals, well, it says proportional to the size. The population size is p, and, well, to be proportional to something means you're a constant multiple of that something. So in this case, dp dt is actually going to be k times p, where k is a constant. Okay, the other thing to notice is that p is a function of t. It'll depend on whatever it is. So I'm going to say p is equal to p of t. So it depends on t. Another thing I'm actually going to describe here is the following initial condition. And that's going to be that p of 0 is equal to p naught. And p naught is just what I'm going to call the initial population size. So this just says that times 0, the population size is whatever the initial population is, which is kind of obvious, but that's just what I'm going to use here. Okay, so this was the model for our differential equation we just saw, well, the model for our application of population growth, model for population growth with the differential equation. And I'm going to notice something. Notice that if y is equal to e to the x, okay, y prime is also e to the x. So it would kind of actually satisfy this if p is y and x is t, I guess, and also if k is 1. In fact, if we change this to, let's say, 3, what's the derivative of e to the 3x? It's e to the 3x times the derivative of 3x, which is 3, so 3 comes down. Notice since this is y, the whole thing is equal to 3y. So y prime is equal to 3y is the differential equation that y equals e to the 3x satisfies, which looks something similar to this. And in fact, if we generalize this and let that number be k, y equal e to the kt, and in fact, just to kind of remind us more of the application here, what is dp dt? It's k e to the kt, since this is just p, this is equal to kp, which satisfies this. Moreover, if we let p be equal to a constant times e to the kt, well, this works as well. Because dp dt is now going to be the constant multiplied by a derivative of e to the kt, which is k e to the kt. If you rearrange this, this is k times c e to the kt, which is just, you guessed it, p. So this satisfies dp dt equals kp. So I guess we notice basically that this is a solution to our differential equation. But we still haven't considered the initial condition. P of 0 is equal to P0. Now remember that P is a function of t. So we have P of t is equal to C e to the kt. Okay. Also, this right here says P of 0, P of t, P of 0. It's P of 0, that means this is a t value. So what we're going to do now is we're going to let t equal 0, and we're going to see what happens. When you let t equal 0, you get P of 0 is equal to e, well, I guess c e to the k times 0. That's just e to the 0, which is 1, so this is c. P of 0 is P0, so we've actually solved for our constant c in our solution. Our solution was this. We now know what c is, so plugging it in, we get P of t is equal to P0 times e to the kt. And this is the solution to the differential equation. Okay, so now I'm going to show that y equals 1 plus c to the t over 1 minus c to the t is a solution to this differential equation y prime equals 1 half times the quantity y squared minus 1. And basically we're going to have to check this by plugging this supposed solution to each side of the equation. So there's a left-hand side and a right-hand side. We're going to check the left-hand side first. Okay, so to check the left-hand side, we're going to have to take the derivative, because the left-hand side is just y prime, of this. And to take the derivative of this, we have to use the quotient rule because it's a quotient. So it's going to be all over the bottom squared. Derivative of the top times regular of the bottom minus regular of the top now times the derivative of the bottom. Derivative of the bottom is 0, and then that's the same. So that's going to be negative c e to the negative t. To the t, not negative t, sorry. Misspoke. There we go. Okay, now double negatives here. This times that, there's a double negative, so we don't have to worry about distributing the negative and distributing this. We'll just distribute this. Here we're going to, of course, distribute this. And let's see what we get on top. Bottom, of course, I'm going to leave the same. On the top, we'll get c e to the t minus, I guess, c squared e to the 2t. And this is going to be plus c e to the t plus c squared e to the 2t. And I think what we'll notice now is that these guys cancel. These two will actually combine to 2c e to the t. So we get 2c e to the t over 1 minus c e to the t squared. And now I'm going to clean this up and just write all this, write the result anyways over here. Okay, so now that we have all this written here, our result from the previous thing, now we're going to plug y into the right hand side and let's see what we get. So we go 1 half times this squared. I'm just going to square the top and bottom individually if that's okay. That's how you square a fraction after all. Just like that. And then minus 1. 1, of course, as a fraction is 1 over 1, so I'm just going to multiply top and bottom by this denominator to get a common denominator. And now what we're going to get, actually, it's going to be a little bit to write, but it's going to be all over the bottom squared, because that's going to be the common denominator, right? The numerator is going to be this squared, so expand it out. That's 1 plus 2c e to the t plus c squared e to the 2t. Looks kind of familiar. And why it's that, of course, is because when you square a binomial, there's the first one squared, and 1 squared is still 1. 2 times their product is 2c e to the t. And then the second one squared is c squared e to the 2t. And now it's going to be minus this. I'm going to expand this out in a very similar way, and it's going to be the exact same thing, only the middle sign is going to be negative. So it's going to be 1 minus 2c e to the t plus c squared e to the 2t after expanding that out. And then after distributing this negative into each of these three, like that, we're going to get negative 1 plus 2c e to the t minus c squared e to the 2t. And what do you notice happens? Well, again, there's cancellation. The 1's cancel. The c squared e to the 2t's cancel. These combine. What do they combine to? They combine to 4c e to the t. But of course that's okay because we still have this 1 half on the outside. And 1 half times times 4 is just 2. In other words, 2 goes into 4 twice. And we're exactly left with what the left-hand side is. So the left-hand side is equal to the right-hand side. And that's one way to check. In fact, that's the best way of checking. That's the most complicated really that it gets, is you have to plug your solution into the left-hand side, right-hand side, see that they simplify to the same thing, and then that's a way to check your solution. Right, so this is a problem from the homework. This is number 3A from 9.1. We did this one in class actually. I'm going to do B, of course, afterwards, but let's just one at a time, so let's do A first. So it asks for which values of r is y equals e to the rx a solution to the differential equation 2y prime, y double prime, plus y prime minus y equals 0. So first off, we're going to, well, it's a solution. We want it to be a solution. If y equals e to the rx is a solution to this, let's plug it in. To plug it in, we're basically going to check. So we need to find, well, let me write it out. Y is equal to e to the rx. What's y double prime? Well, we need y prime first. So what's y prime? And r comes down. Then we can get to y double prime by taking the derivative of this. R is a constant, it stays for free. But then derivative of e to the rx is itself by chain rule multiplied by another r, so it's r squared e to the rx. So plugging these three into this differential equation, we get the following. We get 2 times y double prime, which is r squared e to the rx, plus y prime, which is just r e to the rx, plus y, which is e to the rx, and I ran out of space, but we want this to be equal to 0. So the first thing I'm going to notice is that they all have e to the rx in common, so we can factor that out. So e to the rx outside of what's left over. Well, what's left over should be 2r squared plus r plus 1, I guess, equals 0. So, from the zero product property, if you have two things that multiply to 0, either one of them must be 0. But e to any power is never 0. I mean, if you graph e to the x, it has a horizontal asymptote at the x-axis. So it never is 0 and it never even is negative, actually. But the point here is never equal to 0. So e to any power is never 0. When is this 0? Well, we have to factor this. So setting this equal to 0, let's actually try to factor it. Can it be factored? Yes, it can. So 2r and r multiplied to 2r squared. The two numbers that I know that multiply to 1, oh, I made a mistake, it's negative. Otherwise, it's not factorable. There we go. So the two numbers that multiply to 1 are 1 and 1, and now we have to change our sign so that the middle term comes out to be r. So if you actually FOIL this out, the only way to make it work is to make this positive, so you get 2r in this multiplication right here, and this one's negative, so this is negative r. 2r minus r is positive r. So these lines are just to show that if you actually go through the foiling process, this is the only combination of signs that will make this FOIL into the original trinomial. Okay, so now finally, setting each of these equal to 0, again using the zero product property, either you get r is equal to positive 1 over 2, setting that equal to 0. You just add 1 to the other side and divide by 2. Here, if r plus 1 is equal to 0, subtract 1 to the other side, r is negative 1. So this is a. These are the values for r, the values of r, for which y equals e to the rx is a solution to this differential equation. So now let's look to see what b asks. Okay, so b asks if r1 and r2 are the values you found in part A, show that every member in the family of functions this thing, y equals a e to the r1x plus b e to the r2x, is also a solution. So really we're just checking that this is a solution where r1 and r2 are the things we found from part A. So I wrote the results we got from part A above. Let's label the first one as r1, the second one as r2. Doesn't matter which one you label as which, by the way. And yeah, let's plug that into this. Of course, doing that, we're going to get y equals a e to the 1/2 x plus b e to the negative 1x, or just negative x. We want to see if that's a solution to that same differential equation, which I don't have written here. So before we do it, let's find the derivatives. So this is the function. Its derivative is, well, 1/2 comes down. There we go. Same thing for the second term, the negative comes down. Now second derivative, another 1/2 comes down for the first term, so that's 1/4 a e to the 1/2 x. Good. Another negative comes out, so finally it makes it positive. B e to the negative x. Great. And now we want to plug it into the differential equation, which was 2y double prime plus y prime minus y is equal to 0. So remember, plug into the right-hand side, left-hand side, the left-hand side, right-hand side. But we're going to only do the left-hand side and show that it's 0, indeed. So 2 times this, it's going to be a lot, but that's fine. So 2 times 1/4 a e to the 1/2 x plus b e to the negative x plus y prime, so 1/2 a to the 1/2 x minus b e to the negative x minus y. Y is a e to the 1/2 x plus b e to the negative x, and hopefully this whole thing becomes 0. Meaning all of these terms are going to cancel out somehow. So let's distribute this 2 over here for the first thing. Distribute this negative for the last one. I don't know why we're here. There we go. 2 or something. So let's see. 2 times 1/4 is 1/2. So that's 1/2 a e to the 1/2 x plus 2b e to the negative x. These two stay the same, 1/2 a e to the 1/2 x and negative b e to the negative x. Here we negate both of these, so it's negative e to the 1/2 x minus b e to the negative x. Let's see what happens. Okay, so these two will combine to negative 2b e to the negative x. And here actually is our positive 2b e to the negative x. In other words, they actually cancel out. So these two combine to cancel this one out. Very similarly, these two are like terms. They're both 1/2 a to the 1/2 x. So they combine to positive 1 a to the 1/2 x. And this is negative 1 a to the, well, a e to the 1/2 x. So these two will combine to cancel this out. And they all cancel out. We get 0 equals 0. So this question mark is actually a check mark. And we've shown that it is also a solution. So that's part B. And that concludes this discussion on 9.1. I'll see you in the next video for 9.3. See you then.